Hello everyone and welcome to a new topic or a new course, polyphase systems and specifically three-phase circuits. Let's start. In this course or this topic we are going to cover the advantages of the three-phase circuits, configurations of the three-phase circuits, three-phase power, and then we are going to have highlight about unbalanced three-phase system. So what are the learning outcomes of this topic? By the end of this topic you will be able to explain the benefits of a three-phase system compared to a single-phase system, describe how a three-phase system is generated, differentiate between star and delta connections in terms of voltage, current, and applications, recognize the relationships between line and phase voltage and currents in each configuration, calculate active, reactive, and apparent power in three-phase systems, analyze unbalanced three-phase circuits using appropriate methods, example per phase and symmetrical components. So we are going to have a lot of examples. We are going to solve problems related to three-phase circuits and power calculations. And we are going to validate the results of these examples through MATLAB Simulink training. So this topic or this course consists of a group of videos. So in video number 1, we are going to answer the question, why three-phase systems outperform single-phase? Let's start. To answer this question, we need a brainstorming or a refreshment for the single-phase power. So we are going to start by this design question. The circuit shows a load consists of 50 lamps connected in parallel. Each takes 40 watt, so in total 2 kilowatt as we can see here. The circuit is fed from a single-phase source. V of t equals 230 root 2 sine omega t. So this means V RMS equals 230 angle 0. So we need to design the circuit with the aid of the table, which contains the relation between cross-sectional area and current carrying capacity. So what we need from you is to design the cross-section of the go and return conductor. So my advice to you to stop the video now and then think for the answer of the design and then resume to see how we are going to design these conductors. So let us resume and look for how to design these go and return conductors. We know that the power P of the load equals I square R or V square over R or VI cosine phi. And the load is resistive, so the power factor is unity, so that one will be VI multiplied by 1. So we can calculate the current now. I equals 2000 over 230, so that one roughly equals 8.7 ampere. So if we look for the table, 4 is not accepted, 6 is not accepted, so we can choose the cross-section which is suitable for more than 8.7 ampere. We can choose 11 or 15. So I can suggest that if you choose 15, that one will be a common cross-section 1.5 millimeter square. But this is not my target. My target is we are going to have a current in this circuit 8.7 ampere. So this means the go conductor will carry 8.7 ampere. So that one is go, 8.7 ampere. And the return conductor here has 8.7 ampere. So in single-phase circuit like this one, you need to design the go and return conductors with the same size. Keep this note in your pocket. We'll need it later. Before we delve in the three-phase system and three-phase power, let's look for the single-phase power nature. I introduced that one before in the Induction Machine course chapter 0 video number 2, AC circuits and AC power review. Here I'm going to look for a circuit like this one. We have a supply V of t and the current I of t for a certain load. This load takes P power, active power, and Q reactive. I'm going to focus on the P, active power. So if you have the voltage V of t equals V maximum sine omega t plus theta V, and I of t equals I maximum sine omega t plus theta I. So the power, instantaneous power, equals V of t, I of t. So if we multiply these two expressions together, V maximum sine omega t plus theta V, I maximum sine omega t plus theta I. And we know from the trigonometric functions or trigonometric identities, if we have sine x, sine y, we can have cosine x plus y, cosine x minus y. So the magnitudes will be divided by 2. Let's apply that one. So that one will be the x and that one will be the y. So we are going to have P of t equals V maximum, I maximum, sine omega t plus theta V, sine omega t plus theta I. So we can make a reduction for that one. V maximum I maximum over 2 cosine 2 omega t, right? 2 omega t plus theta v plus theta I. Cosine theta v minus theta I. That one is a number. That one is a function of time. So we know that 2, I can write it as root 2. So that one can be represented by VRMS, RMS, cosine 2 omega t plus theta v theta I plus cosine theta v minus theta I. So if we multiply that one here and that one there, so we have a constant value and we have function of time, double the frequency of the supply. So if the supply is 50 hertz, the power has a waveform with 100 hertz and shifted by this value. And this is what we call it the average power. So the average of this waveform is VRMS, IRMS, cosine theta v minus theta I, and that one we call it the power factor, cosine theta v minus theta I. But what we notice here, the second comment, that the single phase power is not a constant function of time and shifted by a DC level or DC component. And this is what we have as average value. Still we have function of time. Can the three-phase power solve this problem? We're going to see. We proved mathematically that the single-phase power consists of two terms. One of them is a sinusoidal function with double the frequency component, and the second one is the DC level, which represents the average power. We need to prove that one using simulation. So we are going to return back to this circuit. We have a supply with 230 volt, root 2 sine omega t, and feeding a load of 2 kilowatt resistive. So we are going to simulate this circuit and look for what the power looks like. So we are going to move to the Simulink platform to look for this problem. But before moving to the Simulink, I advise you to go to the induction machine course, chapter 5, video number 2, dynamic simulation using Simulink, to see how we are going to set up a model. So now we can move to the Simulink. As you can see here in the right hand side, this is a circuit we want to simulate. A load consists of 50 lamps, takes 2 kilowatt connected to a single phase source, 230 volt RMS value. Definitely we need a meter and voltmeter. I'm not going to simulate the circuit breaker because we are going to take the results at steady state. But before you start your simulation, please don't forget to go to modeling and adjust your model settings. If you don't know how to do it, please refer to the induction machine course, chapter number 5, video number. Back to our simulation and look into the left hand side. So the circuit looks sophisticated. Actually, no. We have just a source here and a load. All other stuff are measurements to validate the results. So if we click here for the AC voltage source, so the MATLAB wants the peak amplitude, so I'm going to add here 230 root 2 and the frequency is 50 hertz. I'm going to connect that one to the load, so I'm going to grab from the library here RLC load. I'm going to adjust the voltage 230 volt, 50 hertz, active power is 2000 watt, inductive reactive power 0, capacitive reactive power 0. So I'm going to measure the current, and we can see the current in this scope if we like. And we are going to measure the voltage. We can see the voltage in this scope. But if we want to have the current and voltage magnitude and angle, I created here two subsystems. Let's look for that one. So we have here a block called Fourier. So if you click on that one, you are going to adjust the frequency to the fundamental frequency. Select harmonic number 1. That one can give you the magnitude and angle for this current. But that one is magnitude. I want the RMS, so I'm going to adjust that one by 1 over root 2. I did the same for the voltage. What this one? So you can grab from the library as well a power block, and that one can measure for you P and Q direct. But here I can take the current multiplied by the voltage I of t multiplied by V of t, then take the average. So there's a block here, it's called the mean, give you the average for this signal. So if we click here, so the mean, you are going to adjust the fundamental frequency 50 hertz. So we expect to see the results here 2000 watt. What this scope shows to you the instantaneous power. So now it's time to simulate our model. We are going to click on run. So we hear a nice sound now that the simulation is finished. So the current is 8.7 ampere, angle 0, the power measured using this method, which is V of t multiplied by I of t and then take the average, is 2000 watt. The power using the block graph from the MATLAB is 2000 watt, Q is 0, the voltage is 230 volt, angle 0. So we are going to look for this scope now. Let's click on that one. So as you can see here, the power oscillates between 0 up to 4000 watt. This means that the waveform is shifted towards the positive direction, and the DC component is 2000 watt here. That one is easy to detect from the figure. I'm going to show you another method how to find the exact value. But if we look for the frequency here, so the wave repeats itself from 0.01 to 0.02. So this means that the periodic time is 0.01. So the frequency of this waveform is 100 Hertz, double the frequency of the supply. The supply frequency is 50 Hertz. So this waveform is 100 Hertz. So the power waveform contains two terms. One of them is a function of time with double frequency component, and another one is average power, which is 2000 watt here. So there is another method if we like to check this power. So we are going for this block. Definitely are not going to forget to add that one to your simulation, which is the power graphical user interface block. So I'm going to click on this one. If we click this one, we are going to find solver, tools, preference. I'm going to click on tools. FFT analysis. If I click on FFT analysis, I'm going to find the waveform of the power. But how do you know? How do you make the link between this FFT and your simulated model? So I'm going to show it to you. Back to the power scope and go to settings, logging. You are going to find a variable name. Put any variable name you like, but the MATLAB should accept. And choose structure with time. So I choose P, which stands for power, and that one is a structure with time, and you do the simulation. So this data will be logged inside this block. So I'm going to this block again, tools, FFT. I'm going to expand that one. So we have here all the scopes have data. So I'm going to choose P. So that one shows to me the waveform. I'm going to choose a starting time, so I choose 0.02, any value, and number of cycles. For example, I'm going to choose one with fundamental frequency 50 Hertz. You are going to find here a red color shows to you one cycle from the fundamental frequency, and that one proves to you we have two cycles from this waveform. So this means we have here something like 100 Hertz. So the maximum frequency is 1000 Hertz. So I have options here. Either I'm going to show the results as a list, or I'm going to choose as a bar. So I'm going to choose that one as a bar first. I'm going to display. Once I display that one, I have DC component by a value 2000 watts, and I have the component at 100 Hertz. So these are the frequencies of this waveform, and that one proves that we have two terms in this waveform. One of them is a DC component and another one at 100 Hertz. So let's go for the list. So in the list, you are going to find that one, display. You are going to find DC component 2000 watts, and if you go to 100 Hertz, you are going to find a high percentage. So the majority of the waveform is at 100 Hertz. So we confirmed that one using list or bars. So now we can see how to build this circuit. So I'm going to close this one. I'm going to open another file. So includes the components we need. This one is a voltage source, meter, voltmeter, product, scope, mean, and that one is a block I told you about that includes the Fourier, and that one is a display. So what we are going to do, don't forget to bring graphical user interface from the SimPower system. So you are going to look for that one in SimScape. You are going for electrical and going for a specialized power system. If you're going for fundamental blocks, you're going to find that one. So drag that one and drop it here. So we have the source. I'm going to connect the source to that one directly here. And then we're going to connect the ground. So that one is a ground. I'm going to connect it to this one and another ground. Right click for that one, copy paste. So that one give you another one. So we are going to have the circuits finished. But to have the measurements, we are going to add a voltmeter across that one. So the voltmeter will be here, there, and we are going to add a scope, for example. And to add the ammeter, we are going to rotate Control R. So that one will be there. So I'm going to connect this one, for example, here. This one is there. I'm going to remove this wire so the emitter will be in series. Another scope will be there. We're going to have the multiplier. So we are going to multiply the voltage signal and the current signal. We're going to have the average. And please don't forget to adjust the block frequency so we can have a display here. And then we are going to measure, for example, the voltage signal, and we can have a display to measure the magnitude and angle. We can do the same for the current. We noticed something. After we adjusted the model, we can run that one, and that one should give you the same results. We notice in the previous model here, we have a circuit here. How do you add it to your model? So I'm going to explain to you how to add something like image or picture to your model. So step number one, you need to make sure that the image you like to add in the same folder that you have this file. So I have here a file called single phase 2. So I need to make sure that the image I want to add here in the same folder. So what we are going to do now, we are going to have a copy from this one, or whatever, any block. So I'm going to make Control C, Control V. So I duplicated this one. I'm going to move it away. And then I'm going to move the main file or the main components, which I'm going to simulate later to have the results. So what I'm going to do, I'm going to select this one, right click, create subsystem. So we have here a subsystem. I'm going to expand that one. So that one shows to you what's inside. I'm going to make it bigger, right? For example. So what we're going to do, I'm going to right click on that one, mask, add icon image. So I'm going to add icon image. I'm going to browse from this one. I'm going to select this circuit. Okay. So that one is okay. So you are going to see the circuit here. So you can add here the label, that circuit diagram. So if I write here, we can write circuit diagram. But there is a problem here. When you are going to run your model, that one is going to give you an error because these scopes are duplicated. So what we're going to do, I'm going to remove that one from the subsystem and then going to return back. So I succeeded to have image here without anything inside this block. I can do something else. I'm going to mask, edit icon image, browse. I'm going to add my photo if you like. So, okay, so I can see myself inside. So I can adjust that one here. So that one is a file I created. Also for this one, for example, that one is a measurements for voltage. So I'm going to add mask, add icon image, browse. In the same folder, I have here something like this voltmeter. So this voltmeter will be added here so I can see the voltmeter. So in this case, you can adjust your simulation. If you have different blocks and you want to add the real image, you can adjust. Also, you can add some effects here, something like shadow and so on. That one from the list here, that's for formatting. But that one, how to add image to your. So now it's time to return back to our slides to check the three-phase power. So what the conclusion from these simulations? For return back to this circuit, so we have the go conductor and return conductor, they have the same size, and the power or instantaneous power is not constant. So I presume that we can answer this question now. Why is three-phase circuit? For the same ampere, a three-phase circuit provides greater power density than a single-phase one. So the power is multiplied by 3. As a result, most electric power is transmitted using polyphase circuits, three-phase circuits to be specific. Second point, it keeps wiring size and costs lower compared to single-phase circuit for the same power density. This point is not clear. So let's recall our design problem. If you remember, the current was 8.7 ampere. So this is the current for the go wire and return wire, 8.7 ampere. So if we look for our table, we choose either 1 millimeter square cross section or 1.5 millimeter square. So assume I choose 1 millimeter square for the go and 1 millimeter square for the return. In total, you have 2 millimeter square. So for this current 8.7 ampere, assume we can call it 9. So if we divide this 9 ampere by 3, so we have 3 ampere per wire, so we can choose from this table 0.5 millimeter square. So multiplied by 3 wires, we have 1.5 millimeter square in total. Different 3 wires, but in total 1.5 millimeter square, which is smaller than 2 millimeter square for the single phase circuit. From another perspective, we are going to keep the size 1 millimeter square, so the maximum current for single phase circuit is 11 ampere, but for the 3-phase one, we can multiply that one by 3 and we can have 33 ampere. So definitely we have here gain in the size and cost. Point number 3. In a 3-phase power system, load balancing is more easily achieved, which reduces harmonic currents and decreases the requirement for oversized neutral conductors. And in some cases, we can avoid the neutral conductor. I'm going to prove that one at the end of this video. Last point. Balanced 3-phase system provides rotating magnetic fields. We proved that one in the previous course, Induction Machine course, chapter number 2. But for single-phase source, we have pulsating field, as we notice in the MATLAB Simulink. So the power includes 2 terms. One of them is function of time by double frequency component, and the other one is the average value or the DC component. So we have pulsating field, more noise for single-phase motors. Now we can conclude why 3-phase systems outperform single-phase one. Conductor advantage. A single-phase system requires a go and return conductors of a full rating, but a balanced 3-phase system requires neutral wire with reduced size, and in some cases neutral wire can be avoided. Power density. A balanced 3-phase system requires 3 wires, hence a 3-phase system is capable of transmitting 3 times the power for only 1 additional wire. Regarding power delivery, a 3-phase system delivers constant instantaneous electrical power. We are going to prove that one mathematically at the end of this topic. Whereas a single-phase system delivers a pulsating power. We proved that one mathematically, and we confirmed that one using MATLAB Simulink. In this case, you have double frequency component. So if you are going to feed a motor from 3-phase supply, you have a smooth torque. While if you are going to feed a single-phase motor from single-phase supply, you have double frequency component and you have a noise, and in this case, that one causes shaft torque fluctuations. What will I watch in video number 2? In video number 2, we are going to see how 3-phase system is generated. See you in the next video.